Ladies and gentlemen, in the left corner with an unknown imaginary weight hailing from the complex domain, we have I to the I to the I. His opponent, also with an imaginary weight and also hailing from the complex domain, is also I to the I to the I? Nevertheless, an epic battle is about to take place to determine what these competitors are equal to and who is bigger. Let's get ready to rumble! Alright, now that the dramatic introduction is out of the way, let's focus on our goal in this video. To see what these two seemingly identical expressions are equal to and which one is bigger. Right out of the gate, we should realize that although the two expressions look nearly identical, the position of those parentheses plays an important role. Let's just see what happens when we use numbers in the real world. If I replace I with, say, 3, the expression on the left would become 27 cubed, or 19,683. The one on the right would be 3 to the power of 27, and that is equal to, hang on, let's give ourselves a little more room. 7,625,597,484,987. In other words, a much bigger number. So it's clear that the placement of the parentheses is extremely important. Maybe the same thing will happen with our two imaginary competitors. Let's find out. We'll start with the expression on the left, since it's the easier of the two. First, we can use an exponent rule. A power to a power means we can multiply the powers. So we get I to the power I times I. But I times I is just -1, so we get I to the -1. That would be 1 over I. Now typically we want to write complex numbers in standard a plus bi form, so we can just multiply top and bottom by I. Since I over I is just 1, multiplying by this quantity won't change the value, only the form. We'll get I over -1 or -I. So the left expression is just -I. Now let's work on the one on the right. This one is going to be a bit more difficult. Let's focus on the expression in parentheses. What exactly is I to the I? We need Eulers' formula to help us out. This amazing formula is the gateway to higher mathematics, including complex analysis. But first, let's take a tiny tangent and let me quickly show you one of the most celebrated equations in all of math, which we get using Eulers' formula. If we just let theta equal pi, then we get e to the I pi equals cosine pi plus I sine pi. Notice that cosine pi is -1 and sine pi is 0. And we get this magical little identity, widely regarded as one of the most beautiful equations. Now let's return to Eulers' formula once more to figure out I to the I. Now the trick for figuring out I to the power of I is to replace theta with pi over 2 this time. Since cosine pi over 2 is 0 and sine pi over 2 is 1, this simplifies nicely to I. Next, let's raise both sides to the power of I. Once again, a power to a power allows us to multiply the exponents, so I times I is -1, and we get e to the -pi over 2. That expression, amazingly, computes to a real number, approximately 0.207. So we can now replace the blue expression with e to the -pi over 2, which looks worse than what we started with. But wait, I'm going to use the I over I trick again and insert it into the exponent. Let's bring an I out of the parentheses. But we know what I to the I is. We just calculated it. So let's replace I to the I with e to the -pi over 2. What now? I want to get this back into an e to the I theta expression to use Eulers' formula again. So let's simplify the exponent in blue by writing 1 over I as -I. And now just rearrange the exponent a little more to get this. This is exactly what we want, an expression in the form of e to the I theta, where we'll set theta equal to the stuff in blue. Here's Eulers' formula once again, and now I'll replace theta with the blue stuff, namely pi over 2 times e to the -pi over 2. And this is an exact expression for I to the I to the I. Pretty awesome. Now, we can calculate this to get a numerical expression in a plus bi form. That comes out to approximately 0.947 plus 0.321i. You can easily verify this on your calculator. That's pretty remarkable if you think about it. An expression purely in terms of I is somehow able to spawn a real component. So it's now pretty clear these two opponents are definitely not equal to each other, but they are both complex. So how do we figure out who's bigger in the complex world? We go to the complex plane. Recall that we plot the real part along the horizontal axis, which we call the real axis, and the imaginary part along the vertical axis, which is called the imaginary axis. The first expression we evaluated to be negative I, shown by the red dot. It has real component 0 and imaginary component negative 1. The second expression we evaluated to be approximately 0.947 plus 0.321i, which is shown by the blue dot. So how do we know which is bigger? A reasonable approach to assessing their size would be to find their distance from the origin. This makes perfect sense. After all, on a regular one-dimensional number line, the distance of a number from 0 represents its size. When working with complex numbers, we call this the modulus. The formula is easy. For a complex number z equals a plus bi, the modulus, denoted by the absolute value symbol, is the square root of the sum of the squares of the real and imaginary parts. In other words, it's just the Pythagorean theorem. You can confirm for yourself by plugging in the values of a and b that in both cases, their respective moduli are equal to 1. Let's draw a circle of radius 1 from the origin to see if this is true, at least visually. Yup, both complex numbers have a modulus of 1. So to summarize, although the two expressions have different values, the modulus of each is identical. And we just showed it's equal to 1. And that means they are the same distance away from the origin on the complex plane, so that's going to bring this epic battle to a close. Which means that our dueling powers of I will have to settle for a peaceful tie. Let me know in the comments below if you know some other amazing applications of Eulers' formula. And be sure to subscribe for a new video every week featuring puzzles, problems, applications, and explorations. Thanks for watching, and see you soon.